found that in 2.4. We found that in example 4. When we had the function 1 over a, right? The slope of it we showed was negative 1 over a squared. Okay, we did that like using that formula in the purple, and that's what we did. That we did in chapter 2 is like literally the basis of everything we do in calculus. Okay, because what we found there was the instantaneous rate of change at any point. So again, this term, instantaneous rate of change, and that formula in the purple, they have to be like synonymous in your mind. Okay. The study of rates of change of functions is called differential calculus. And what we did there when we had f of x equal 1 over x, and we found that the slope was this, what we actually found was the derivative. Okay, that was the first time we found a derivative, right? So let's talk about what derivatives are. The first thing I need you to, again, sort of associate in your mind is this. Derivative, right, that term means slope of the tangent line. Okay? It also means rate of change. Okay? So derivative is slope. Slope is derivative, right? So what's derivative?
Slope.
What's slope? Derivative. And what else does slope mean?
Rate of change.
Rate of change.
Wait, but it's the rate of change is tangent?
It's the rate of change of a quantity at the instantaneous rate of change of a quantity. It's the slope of a tangent line. Okay, notation, right? There are several ways to write derivative. One is this, right? It's f with an accent mark. We call that in math prime. Like remember last year was theta, theta prime. I don't know if you ever did that. So it's read f prime of x, right? And you read it like f, and you write it f prime of x like this. Another one is y prime. So you have y, and then when I write y prime, I know that that's the derivative of y. dy dx is another one, okay? dy dx is how you read this one. You don't say over or divided by, it's just dy dx. And it literally means the derivative of y with respect to x. So what exactly is dy dx? Remember, our function can be written as y equals something. dy dx is taking d dx of that. So it's like you have the y, d dx on its own is its own thing, and then together it makes dy dx. So just like when you first learn math, you learn about these like silly little symbols, right? Like what are these? Like to somebody that's never seen math, these are just like scratches, right? But you've come to know them as, you know, symbols that do an operation, right? They're called operators. So when you see a number and then that silly little thing and this, you know to take the numbers and add them to each other. Similarly, the ddx on its own is an operator. It's like a plus or a minus or a division symbol. So when you see that in conjunction with some other function, f, you know to take the derivative of that function. So this will be read as df dx. And then another way to write it is like this, ddx of f of x. Okay, all these are different ways of writing the same exact thing.
So derivative is kind of like the concept behind the equation, like when it's
Yeah.
zero.
Right.
Okay.
That equation we said was the slope of the tangent line. In short, it's the derivative.
Okay. So it's the same thing.
It's the same exact thing.
Okay.
Okay. Speaking of which, good segue to the definition of the derivative. This is it. The definition of the derivative is exactly this, which we've done thousands of times now. And until now, if you realize, we never really knew. I never really told you what to call this thing. And people would be like, okay, do we call this m equals? And I was like, yeah, whatever. It was my way of sort of like deferring that question to now. Now we know what to make that. It's f prime of x, right? Because it's really, we don't use m, we use f prime.
What's prime again? I forgot.
Prime just means derivative of f.
Derivative of x?
F. F. Okay? So, now, some new vocabulary. So, the derivative is this, provided that this limit exists. Right? Remember, anytime we take a limit, there's the danger of it, becoming like DNE or something. If f prime exists, we say that f has a derivative, or we say f is differentiable. So differentiable, has a derivative, are the same thing. Okay? Differentiable means able to be taken the derivative of. A function that is differentiable at every point in its domain is called a differentiable function. Don't focus too much on that. Just focus on this, that if there is a derivative at a point, we say that it's differentiable at that point. Okay. Huh? Differentiable. Sure you can. Differentiable.
Differentiable.
Right. Right. It's like
All together now.
okay. Now, look at this. Differentiate, right? Or differentiate in as like tell it apart from something, right? But in math, differentiate means find the derivative of f of x equals x cubed. Okay, so here's what we're gonna do. F prime of x, right? So now we know this is gonna be f prime of x, right? Find the derivative means find f prime of x. So f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. Now, the further, we progress and stuff, you can skip writing this one. You can just go straight into the function itself, right? So this is going to be limit as h approaches 0, x plus h cubed minus x cubed over h. Okay? Now, I actually debated for a long time whether or not to leave this problem in here, but then there was no other way, so I just left it in here. Okay, so now, because all the other problems were already used up. Anyway, so here we have to do this operation. Okay, x plus h cubed, it has a formula to expand it, but if you don't remember the formula, which most people don't after Algebra 2, especially if you're on Zoom for Algebra 2, we can just do it by hand, right? So let's just do it. X plus h cubed is x plus h multiplied to itself 3 times. Okay? So this is, if I multiply this, just foiling it, there you go, plus h squared. And then multiply by x plus h. Okay, you're not going to have to do this too often, right? This is going to be, okay, so distribute the purple x cubed plus 2x squared h plus xh squared plus x squared h, 2xh squared, h cubed. Okay? So, let's put that in here. There's going to be some like terms to combine. So what is that? X cubed plus, look at this, 3x squared h plus 3xh squared plus 1h cubed. Okay, minus x cubed all over h. Just like before, same black magic as before, right? Everything has to go away, including the h by the end. So look, x cubes cancel. So now I've got this. Okay, let's factor out an h. H, 3x squared plus 3xh plus h squared over h.
Wait, was the minus x cubed at the end already there?
Yeah, it's this.
Oh, right.
The h's go away, and now can I put the h equals 0 in there?
Yeah.
So I get 3x squared. Okay, so all that to say f prime of x is 3x squared. Okay,
You plug in
that was at any point. Now let's do another problem.
specific one.
We're going to use this to find the derivative at the indicated point. Remember in the, like on the test, you also had, you know, a equals whatever. So now we have a equals 2. So now we're going to do,
Use a or x?
okay, so look,
X is so much better.
no, listen. So now it's going to be f prime of x at x equals 2. So this is going to be the derivative at x equals 2. So that's how I write it. This is the derivative at 2, not at any point x. And this is going to be f of, the limit first.
Wait, how do we know the
5 points on.
It's said here. It's f of 2 plus h minus f of 2 over h. So this is limit. H approaches 0. F of 2 plus h, right? 2 plus h squared. Minus f of 2, what's f of 2? 2 squared plus 3. All over h. Yep.
So black magic.
Okay, so now, expanding this, I get 4 plus 4h plus h squared plus 3 minus, how much is that?
4 minus 3.
4 plus 3, 7.
Oh, you're right.
Over h. So look, this is 4 and 3, right? That has to be a 7 because it has to cancel away with it. Okay? And now, take factor out an h.
Can we get rid of the like numbers without variables?
Yeah.
Okay, sorry.
Yep. 4 plus h over h. So this is, cross out the h's. Limit, h approaches 0, 4 plus h, which is 4. So, therefore,
Is f prime?
okay. All right. So now, the whole h thing, I get it. It was fine at first. Now it's kind of, getting old. It really is getting old. So, you know what? H is something we had added into the problem, right? And then you think to yourself, well, is there a way to circumvent H altogether and not use it? Well, guess what there is.
Oh my.
Remember what we had said before. Before I had said there was an X, right? Then we went an H unit over to X plus H, right? And that's where the whole H thing came from. Well, why do that? Why not just call them different things? Why not say, here's a point A, here is a point X. Let's just look at what happens when X gets really close to A. So we're gonna reword the whole thing, eliminate the H. And when you eliminate the H, all you say is, okay, let's make, because remember what we're doing is we're bringing this point closer to that point, right? In doing that, this X value is going to get closer to A. So now, the way to eliminate the H is you rewrite it like this. So now there is no H.
So is this a new equation?
That's a new equation that doesn't have the H.
Are we getting rid of the old one?
For now, yeah.
That's like the T1.
This
So,
is just this
on
is
the-
average rate of change thing.
Yes and no. So on the test or quiz, I'll specify which formula I want you guys to use, okay? So I'll say, okay, given this formula, blah, blah, blah. So it'll be like this. Using the definition this, find that. Okay, so that's what we're gonna do now. So okay, so A is 2. So we want to find f prime of 2. This is the limit as x approaches A, meaning x approaches 2. F of x minus f of A is f of 2, right? Because A is 2, all over x minus A.
X minus 2?
Thank you. So, now I want to erase for some reason. Okay. So now this is the limit as x approaches 2. F of x is just this, root x minus 1. Minus f of 2 is the square root of 2 minus 1. All over x minus 2. So this is the limit as x approaches 2. Root x minus 1 minus 1, right, over x minus 2. Okay, if I plug in x equals 2, I get 0 over 0, so this is not going to work. Okay, we've learned a couple of ways to get rid of the 0 over 0 indeterminate situation. One was factoring, another one was, you know, the fractions, right? You kind of multiply top and bottom by the denominator. This one, because it's got a root plus or minus a number, you have to multiply by what we call conjugate. Okay, here's what we do. Wherever the root is, right, you go over there and look, this is the square root minus 1. You multiply by the square root plus 1, top and bottom. Okay, now, okay, so now look. Look at what you have here. Something minus something, something plus something. So A minus B, A plus B.
Wait, is it x minus 1 still, or is it?
Yeah, it's because it's the identical root minus 1, the identical root plus 1.
So does it just become like
So now look, A minus B, A plus B. How do we do it? You square the first thing. So square this, what do you get? X minus 1 minus square the 1, 1. Over. Okay, here's the part where everybody's going to want to distribute, but please don't distribute. It's going to be x minus 2 in parentheses like this. Okay. Don't distribute, because look at what happens. What do you have on top?
X minus 2.
And then x minus 2, x minus 1, yep. Look, these have to cancel. That's why we don't distribute. So limit, x approaches 2. What do you have on top? Over x minus 1 plus 1. Okay, now it's safe to plug in the 2. 1 over all that, which is to say this is 1 over 2. So f prime at 2 is 1/2. Which means when you draw that, you don't have to do this, but just to root x minus 1, this is how it looks. Okay? If you go to x equals 2, the slope there is 1/2, right? And you can see like that could, right? So that's what we just did, okay? Okay. All right. What is this saying here? What do we need to find? ddx is what? Derivative, right? When a equals -1. So we're going to do the same thing. Yeah. This time, though, you write it as is. Let me, yeah.
I'm gonna interrupt that thing, but I don't get how you got 1 over 2. It's square root of 3 plus 1.
2 minus 1. This is 2 minus 1. So this is how this looks, right? The limit as x approaches minus 1, f of x minus f of a, which is negative 1, x minus a, which is x plus 1. Okay, so limit as x approaches minus 1, f of x.
Minus one,
No, I didn't say you.
minus one is a negative.
Yeah.
Oh, okay. I didn't know if it was like one from the negative.
So 3x squared, that's f of x, minus, what's f of minus 1?
3.
3.
Yes.
Okay?
Yeah, down.
Over x plus 1.
How did you do 3?
So it's,
3 times 1.
yep, okay. Okay, so now, what happens if we put in a negative 1? You get 0 over 0. So that's not going to work. That means okay, so this, we can only factor this, right? So if I take out a 3 here, I get x squared minus 1. But when I factor that, I get 3, x minus 1, x plus 1. It's got to cancel. So now, this is 3 times negative 1 minus 1, negative 6. Okay. Now, let me show you guys some other notation. Because
Wait.
what? Okay, hang on. I'm going to show you. Okay, so check out what we did. This is ddx of 3x squared. Okay, now watch the notation, clever little notation. Vertical line means evaluated at equals negative 1 equals negative 6.
Wait.
That's what you have to do for DDA.
Yeah, so this is proper notation. Now look, on the answer space, if you just wrote negative at negative 6, it would be okay. But I do want you guys to know this notation as well, because you're going to see it everywhere.
Yeah.
This says ddx of 3x squared. And then how would you put in the negative 1? Because it can't be f prime of negative 1, right? ddx of 3x squared evaluated at x equals negative 1 is negative 6. So this vertical bar means evaluated at in math.
3x squared next to the numerator?
Yeah,
Oh, next to the numerator.
next to the numerator.
So can we
Or it could, hang on, sorry. It could also be like this. It's not a deal breaker, yeah.
So can we only really use like the f prime when we're given the a value?
No, you can use f prime when your function originally was labeled f. Like, you can't call this f prime because you don't know that the original function has a name of f. What if the original function was g, or h, or s, or t?
I mean, I think my question is more just like we can't use this equation if we're not given like the a value.
Oh, the equation, like
Yeah.
this equation, correct.
Yeah. Okay.
If you're not given the a value, then it'll just be like in,
Then it'll be like the h one.
Can you just explain the answer notation again?
yes.
Yes.
So these are extremely important because what just happened here? Okay, so the next page is extremely important because this shows like understanding and application of the slope and the derivative and all that stuff. Okay, so because we said the derivative at a point is the slope, right? We can get a good idea of what the graph of f prime looks like when you just have a graph of f, okay? So take a look at what we're going to do. we're gonna estimate the slopes of f, and we're gonna graph f prime. So here, first of all, you have a function, and this is the original f of x, okay? Here, we're gonna graph the derivative, which is f prime of x, and what's another word for derivative? The slope. So here, please, on the y-axis, can you just make that a y prime, right? On the y-axis, that label there, make it a y prime. Okay, take a look at what happens here. The easiest case, the simplest case when we're doing this is when we have a graph that is all segments, because when they're linear segments like this, it's so easy to find the slope, right? Because we've been finding slopes of this since like pre-algebra. So I have here 1, 2, 3, 4 different segments, okay? Take a look at the first segment here. This segment lives in the interval from x equals 0 to x equals 1. All right, and what's the slope of that? 3. Okay. The next one, what's the slope? 0. The next one here, what's the slope? And then finally, the last one? 1. Okay, so here we're going to go on this chart. I mean, on the other grid. So from this blue one lives only from 0 to 1. And the slope is a constant 3. So you go up to 3, put a point, a slope of 3 from 0 to 1. Now, don't ask why just yet, but at the end of this, we're going to put an open circle. Okay.
When do we ask why?
You don't have to, because I'm going to tell you.
Okay.
So the next part is m equals 0 from what to what?
1 to 3.
From 1 to 3, m equals 0. Open circles, open circles. And then,
Oh, I get it.
We don't.
then it's a 2. Then it's a 2 from 3 to 4. Again, open circles. And then it's a 1 from 4 to 5. Open circle, and then closed circle at the end. When you do these, the first and the last points are going to be closed circles. Everything else is going to be open circles in the middle. Because at x equals 1, you can't have one or the other, right? We're going to talk more about this in section 2 or 3. Okay? So just remember, closed, open, 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 and then closed. Okay, so that's all you need to do for that. Yes, well, it depends. It could also be if this is position, that could be a velocity. If this is position, that's velocity. If this is velocity, that's acceleration. Okay, yeah. Yep. Yep. Okay. Yeah.
Why did you do that?
Oh my God, that's a good question. I did that wrong. -2. Okay. All right. Good. Thank you. Okay. Moving on. One-sided derivatives. Shh. Okay. Now, talking about being differentiable, right? A function is differentiable on a closed interval, right? So from A to B, if it exists from A to B, if it has a derivative at every point on the interval, and if the following derivatives exist. So if the right endpoint exists, and if the left-hand endpoint exists. So take a look at this. Suppose you've got a function like this, and like this is some function, and then this is point A, and this is point B. And suppose this function that you're looking at, we're only looking at it from A to B, okay? In order for this to be differentiable from A to B, you have to look at every single point here and make sure it's differentiable. But also, what about the endpoints? You have to see that it's differentiable from the right-hand side if you're looking at this endpoint, and from the left-hand side if you're looking at that endpoint. Okay? All right. Now, let's take a look at where something is not differentiable. Okay. Look at this. It's a segment and then another segment. In the entirety of the left-hand side of this, what's the slope?
-1.
M equals -1. And then here, +1. But then, take a look at what happens here. The slope is -1, -1, -1, and then when it reaches this point, it abruptly changes from -1 to +1, just abruptly. Like 1 second it's -1, the other second it's +1. So if you zero in on that point, and if you look at the derivative from the left, it's -1, but from the right, it's +1. And because it doesn't have the same slope, the same derivative on either side of that, we say this function is not differentiable at x equals 0. It's differentiable everywhere else, but at x equals 0, it's not differentiable. Let me do the other example and then I'll take questions. Okay, so let's write that down. Let's summarize that. The derivative changes, and the word here is abruptly. Okay, from -1 to 1. Where does that happen? At x equals 0. Therefore, this implies that f of x is not differentiable at x equals 0.
So doing right, is that the answer? Or is what's written on there?
It depends. As far as the answer, it depends on what the question is asking you for. Now, if the question is asking, is it differentiable, yes or no, the answer is no. If the question is asking, is it differentiable, and then why, to answer the why part, you have to say this, okay, the derivative is -1 from the left-hand side, and then you have to say the derivative from the right-hand side is +1. This is how you answer the question of why. Okay? So say this to answer why. Okay, before I take any other questions, I'm going to do the other example. Okay? Because it's the opposite way. Okay, so take a look here. It says, is this one differentiable at x equals 0, right? So the question was, is it differentiable? And then somebody answered it and says, yes, this is differentiable at x equals 0. You go to x equals 0. Now take a look at what happens. I'm really going to zoom in here, right? At x equals 0. So take a look. Here's the slope here. And then as you go to 0, we see that the slope is changing. But the slope is changing gradually, not abruptly. And as you go here, there is a very continuous change in the slope at x equals 0. It's not like the absolute value where it, like in a split second, it changed from one to the other. So if I go to x equals 0, and if I were to find the derivative using that formula, the limit, blah, 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 I would see that, right? If I do the math, like we've been doing all day today, the limit from 0, from the minus side is 0, and then from the plus side is also 0. So because the derivative is the same from the left and the right, this is differentiable at x equals 0.
Is it always going to be x equals 0?
No. Because derivatives are equal from left and right.
If they're equal, they're differentiable.
At that point, yeah, if they're equal from the left and right, then they're differentiable. Because, so if you do all of this math of x squared, f of x plus h, well, you get the same number. Let's actually do this one. Yeah.
How do you, when you're actually like solving those problems,
Uh-huh.
how do you like do it differently based on
This. It's gonna be like this, and then it'll be like, so take a look at this one, okay? This is a good one to show. So use one-sided limits to show that the function does not have a derivative at x equals 0. So what we're going to do is for the left and for the right, okay, this is the left function. We're going to